Hello, my dear students. Welcome back to Shortcutmaster. Okay, so this is Srikanth. I hope you are eagerly waiting for my videos. Today, I am going to discuss about the kinetic energy of a rolling body. Okay, so let us see all of you. This one we have a horizontal surface in this figure. Okay, so this body is rolling in the clockwise direction with some angular velocity is omega here. So for this body which is having some mass m, we have to calculate kinetic energy. Now I will determine this kinetic energy in two number of ways. Two methods I will display all of you. Okay. First method is a general or a direct method, and the second thing is nothing but a shortcut method for you. We can determine that one by using only one single step. Okay. At the same time, that will be helpful for you as a shortcut in the GATE and ESE examination for sure. Okay. Yes. Now I'm going for method number one. All of you have some patience. Method number one. Okay. Number one. So actually the thing is the body is moving, rolling in the clockwise direction. For that one, we have to calculate the kinetic energy. Can I say point all of you that the total kinetic energy will be definitely equal to kinetic energy in the translation plus kinetic energy in rotation or not? Definitely. So what will be translation kinetic energy? Half into mv square. What will be rotational kinetic energy? Half into I omega square. Okay. So these actually I am assuming this body as solid disk. Okay, so you know very well all of you for a solid disk with respect to its centroid axis. Okay, with respect to its centroid axis, the value of mass momentum of inertia will be always equal to what? We can take it as simply m into r square by 2. Okay, so I'm writing the value here, all of you, half into m multiplied by v square plus half multiplied by. So what is the value of I? We can take it as mr square by 2 into what will be angular velocity. We know very well tangential velocity is always equal to what? V equal to r into omega. Okay, therefore we can take it as omega will be always equal to v divided by r, we can write. So we can take it as finally v by r whole square. Okay, so finally we can take it as half into mv square plus, can I cancel this r square and r square? Yes, sure. So we can take it as m into v square divided by, we can take it as 4. Okay, so I'm having a small discussion with you. Please try to understand. Can I say a point all of you that this represents kinetic energy in the translation or not? Yes. And this represents what? Kinetic energy in rotation or not? Yes. Can I say a point all of you that this is half mv square, this is 1 by 4 mv square, means what? Your kinetic energy in rotation is 50% of kinetic energy in translation or not? Again I'm repeating all of you, the kinetic energy in rotation is 50% of the kinetic energy in the translation. Both together has to give definitely 3 by 4 m into v square, and this one is a quite and a unique general method, we can say. Okay, now I'm going for method number 2, all of you, that is method number 2. Okay, so here I'm just going for one point for you. You know very well, whenever a body is rolling without slipping, can I say that the point of contact will be always the instantaneous center of rotation or not? The point of contact will be always nothing but the instantaneous center of rotation. That means when a body is rolling without slipping, in this entire body, this is the point at which we have zero velocity. Now what I'm trying to do, I'm assuming that your entire body is said to be rotating about this point I, which is called as instantaneous center of rotation. Now I can assume that this body is having pure rotation about the point I, therefore this body is having only rotation. And since this body is having only rotation, I can say one point for you all of you clearly that kinetic energy, one second, kinetic energy in rotation will be always equal to nothing but half into I omega square only. But the problem here is what you know, only with I value. Okay, so here in the previous case, we have determined the value of I with respect to axis of rotation. But in this case, we have to bring out the value of moment of inertia about this instantaneous center I. What the point of therefore, what I can do in this case, we have to apply the parallax theorem. Okay, so we can apply parallax theorem, all of you. By applying parallax theorem, we can write moment of inertia about any point is always equal to sum of moment of inertia about the centroid axis plus mass multiplied by distance square. Distance D stands for perpendicular distance between I and then C. Okay, so we need the value of moment of inertia about I center. The value about the value of I about the centroid axis is always equal to what, m into r square by 2. So plus we can take it as m multiplied by only r square. Okay, are you getting my point, all of you, my dear students here? Therefore, we can definitely write this value of I with respect to I is always equal to how much? So 3 by 2 multiplied by m into r square is the value. Okay, now I am writing the final step here, all of you. Clearly here, just try to understand. That is half I is nothing but what? We can take it as 3 by 2 into m into r square into the value of omega. Omega stands for what? We can take it as simply V divided by r whole square. R square is getting cancelled. We will be getting this value as how much, you know? 3 by 4 into mv square is the value. Okay, so tell me, all of you, are you getting the value in one single step or no? Yes, but the point is what, you know, you should be able to apply this parallax theorem. Okay, almost the complexity is same, but what I'm trying to do is nothing but I'm just trying to give all the possible methods for you. Okay, a general method and a shortcut method which will be helpful for you a lot in the GATE and ESE examination. So all of you, please subscribe to my channel. Okay, that is Shortcut Master. Thank you, all of you.